Welcome to this next lecture of a series of lectures on solid state. In today's session, I'll talk about the internal structure of crystalline solids, wherein I'll try to focus on the concepts of lattice and the unit cell. What basically I'm going to do is, I'll start by reviewing what we did in the previous session. Thereafter, we will talk about what are ordered arrangements and how do we represent them. In this process, we'll try to work out what's the meaning of a lattice and all. Thereafter, we will try to see what's the difference between a lattice and the crystal structure, because that's very crucial. We'll spend some time on that. Thereafter, we will try to see how do we identify the unit cells in a two-dimensional lattice, and thereafter how do we do the same in case of a three-dimensional lattice. Thereafter, we will try to sum up what we do in today's session. So that is how the session has been planned. Let's make a beginning by recalling what we did in the previous session. In the previous session, we discussed about the different physical states of matter and their interconvertibility. That's how we began with, and we try to talk about solid state as one of the states of matter. Thereafter, we outlined the characteristics of crystalline solids, followed by the classification of the solids in terms of the species which constitute them and the forces of interaction between them. This was followed by kind of a general description or explanation of the laws of crystallography, and we did try to outline the significance of each one of them, that is the Steno's law and then thereafter Hoyle's law. So let's now start with understanding what are ordered arrangements and how do we represent them. Before we move further, let's try to recall what Hoyle said in his law. He said that the outward symmetry of a crystal implies that there is a highly ordered internal structure, and in the process he proposed the existence of a small unit which can build upon to give you an external symmetry there. Let's explore some ordered arrangements. We all come across street lights. That's a common thing which we come across. We know that they are normally put on at regular spacing. Say we have one street light here, another say 50 meters or 100 meters, depending on the requirements of a given stretch. The lights are put in an ordered arrangement there. Similarly, if we go towards the seashore or otherwise, we find that the windmills are also spaced like this in a very regular fashion. We have that, and if we go further there, probably we can even come across what's called as a wind farm, wherein we find that the windmills are arranged in a regular fashion in two dimension. It's a form. So these are different kind of ordered arrangements which we come across ourselves. Now, if I want to talk about similar kind of arrangements are there in case of crystals also. Let's look at the crystal of say sodium chloride. I have just given some kind of a depiction here. So what you see is this is a representation in two dimension. This is a three-dimensional representation. What you find is here again the constituent species, the ions in this case, are regularly arranged. Now, the question comes up is how do we represent such a regular arrangement, because that is what we want to focus on. Let's go back to our example of a street lights. Now, what you see is that just it's a kind of a schematic diagram here which shows that street lights are put at a regular interval there. Now, to represent this, one way could be that every time I want to talk about the arrangement of street lights, I draw them and tell that okay, this is here, this one is here, this one is here, and so on and so forth. Or do we have some other means of doing it? What basically we have is we have an alternative way of doing that. What do we do is, I've taken the same stretch. What we do is to represent a lamp post, I do not have to talk about a lamp post as such. What do I do instead is, I take any part of the lamp post. Say I have chosen in this case, say the bulb here. Okay. So if I take the bulb here and then this bulb here represents this whole lamp post. Similarly, for the next lamp post also I can take the same place here or here and so on and so forth. Alternatively, I can probably take the tip of this lamp post. Same thing I have to do in all of them. So what I do is, instead of drawing the so-called lamp post so many times, what I do instead is I just take some dots, say points there. Each point represents a lamp post. That means from the repeated motif, in this case the lamp post here, I pick up any point, okay, and I pick up the same point in all such motifs, and then try to represent this whole arrangement here can be represented in terms of a series of points like this. Okay. So, such a representation of a regular arrangement is called as a lattice. Let's move further. What does it mean is, we know that say from this lamp post to this lamp post, say it is 50 meters. I don't have to draw a long stretch there. What I can do is, I can have a proportionate size there. Say maybe I can have say this difference to be about 5 millimeter or 5 centimeter or whatever I choose to be. So I make some regular interval here, say I call it as A, as a repeat distance here. So from here, if I put a repeat distance of say 5 millimeter or 5 centimeter or whatever it is, same thing if I keep doing it, I will be getting the next lattice point there. Okay. That means in principle, such a regular arrangement of in one dimension can be represented in terms of a series of points in one dimension. Such a representation is called as a lattice. Let's move further. Now suppose I have got a two-dimensional regular arrangement. In such a case, how do I represent that? So I have got some, say in this case I have taken a representation wherein a dagger happens to be my motif, repeating motif. So to represent this kind of an ordered arrangement, what do I need? I need to locate each of these points there, each of these motifs there. So what do? I choose say a point here, say this point here. Okay. Same thing I have to do in all motifs there, and what I do is, say I start from this point here, I put a point here as a representative of my first motif there. Then if I move certain distance given by this vector here, I come to the next motif, same distance I move here, another one, so on and so forth, I can keep doing it. Similarly, such an arrangement can be given in terms of a two-dimensional arrangement of the points here. So this is a two-dimensional lattice which represents a two-dimensional ordered structure here. Now let's observe here, when I had in the previous case one-dimensional arrangement there, so I had series of points here and I needed only one parameter A, the repeat distance. That means what is the distance between the different motifs there. When I have a two-dimensional lattice, so I need more than one thing here. I need rather three things. One is I need two distance parameters, that means the vectors I need. Say what is the distance in this direction here and what is the distance, repeat distance in this direction here. So I need two distance parameters and one angle parameter. That means what is the angle between the two distance vectors there. Let me just clarify it by taking another motif here. Now I have the same motif but arranged differently. You can see that the pattern is different now. So in this case, I will find that I need again two vectors. That means each vector, the distance of the vector, the magnitude of the vector is a measure of the distance in this particular direction, the repeat distance in this direction, and also the angle I need here. So in this case, what I find is the angle is different from what we had in the previous case. So here again, the basic point is, for a one-dimensional representation, I need only one parameter, that is a distance vector. For a two-dimensional representation, I need two distance parameters and one angular parameter, that is the angle between the two distance vectors there. Let me show you some more two-dimensional lattices here. So the first lattice on the left hand side, what I have is, so I have A is equal to B and angle is equal to 90 degree. That means essentially I am going to have a square lattice. That means if I start from this place, I have some distance A, repeat distance here, here I got distance as B. So A happens to be equal to B, so essentially I am going to create a square kind of a pattern there, because the angle is 90 degrees. I may alternatively have A to be equal to B, that means the two distance vectors are equal, but the angle is not 90. So in this case, I will have a different kind of a pattern coming up there. So this is a two-dimensional lattice of a different kind. Let us take another case here. You may have a situation that A is not equal to B and angle still is equal to 90. So we got a rectangular kind of a arrangement here, or maybe you can have A not to be equal to B and angle is also not equal to 90. So I have different kind of arrangement there. So what we have done so far is, we have seen that a lattice essentially is a representation of an ordered arrangement. If it is a ordered arrangement in one dimension, I will have a series of points separated by a given fixed distance there. If I have got a two-dimensional lattice, I will have series of points spread over an area and they will be identified, they can be generated in terms of two distance vectors and one angle between them. Now, so essentially I am talking about a lattice, and lattice essentially is a representation. Let us try to differentiate what is the difference between a lattice and a crystal structure. Does it represent a crystal structure? The answer is no. So, let us try to recall that a lattice basically is a representation of a regular pattern. It consists of a periodic array of points, and the periodicity of these points is a manifestation or is a representation of the periodicity of the arrangement which we are talking about. And further we can say that each point has identical surroundings to all other points. That means, in a lattice, if I take any point, what is the surrounding things there? I take another point, it will have a similar kind of surroundings. That is the basic premise of a lattice to be a lattice. On the other hand, if you look at crystal structure basically is a periodic arrangement of atoms, molecules or ions in the crystal, because a crystal essentially is made up of atoms, molecules or ions depending on what kind of a solid I am talking about. And then in this case, the moiety that repeats periodically is called as the basis or the motif. And if I now compare the two, so lattice talks about how to repeat, that means what is the regularity of repeat there. On the other hand, basis or the motif is what to repeat. So, to generate a crystal structure, what we have to basically do is, so crystal structure is nothing but the lattice plus the basis or the motif. That means, now look at this, this is just a two-dimensional lattice there. And if I say for this material, whatever I am talking about, this crystalline solid, if this is basically a schematic diagram here. So, suppose this is the basis, that means this is the repeat unit there. So, what do is, I put this repeat unit on each of these lattice points there. So, what I generate is a picture of this kind. This is your crystal structure. So, I hope you understand, crystal structure is how does the basis or the motif repeats, and lattice is just a representation of that ordered arrangement there. So, that is the basic difference between the lattice and the crystal structure. Let us have a simple example here of a two-dimensional lattice of sodium chloride there. So, minus that the green balls here, the green spheres here are representing chloride ions, and this grey ones are giving you sodium ions there. So, this is an two-dimensional ordered arrangement of sodium chloride. That means, if I take sodium chloride crystal, slice it up, and if I look at it in the face, one face, I will get arrangement of this kind. Now, this arrangement can be represented in terms of this kind of a lattice here. So, here I have used two kinds of points here, one are full ones, one are the empty ones there, just to differentiate between, because there are two different kinds of ions there. So, in such a case, my lattice points are not of the same type, they are different there, because each say the bold ones are representing the chloride ions and the hollow ones are representing the sodium ions there. Now, let us move further, I am sure that by now we know what is a lattice. The another thing which I want to focus on to in today's session is about what is the meaning of a unit cell. That is what Hoy pointed out too. What is a repeat unit, a small thing there. We will come to 3 dimension at a later stage. Let us begin with, because it is easier to visualize things in 2 dimension there. Let us try to understand the concept of a unit cell in the context of a 2-dimensional lattice there. Now, suppose this is a 2-dimensional lattice. It is something similar to what we had in the case of sodium chloride there. That means, there are 2 different kinds of repeat things there. Now, question is, so what is the repeating unit here? How do I represent, because one is I have a nice regular pattern there, but how do I represent that in terms of a unit cell? Unit cell basically refers to something small which can repeat in such a fashion, that means, if I translate that thing across in all the possible dimensions, I should be able to generate the whole lattice there. Let us have a look at the next slide here. What you see is that the lattice I showed you, if I look at the square drawn here, this is my unit cell. Why is it unit cell? Because if I take this and translate it further, that means, if I move from here, I come to say this here, and then if I move from here, I generate this one. That means, if I take this slab, this square I have created there, the black color square, if I keep moving in say this direction or in upward direction, if I keep doing that, I will be able to generate the whole lattice there. That means, unit cell should be able to generate the whole lattice on repeating, that means on translating it in the 2 dimensions in this case. But is it the only possible unit cell in this case? The answer is no, because they can have more than that. Let us have a look at it. You may even choose a unit cell like this. So, what do we find is this is similar to what we had in the previous case, but it is different. Let us see the difference here. The difference you see is, in this case what we had is the corners of the unit cell were at, say, the yellow spheres or yellow circles. On the other hand, what we have in the second case now is we have got the corners to be on the white spheres or white circles there. This also can generate the whole lattice. So, this is alternative arrangement. That means, same lattice can be represented in terms of more than one unit cell, maybe yet another one. Let us have a look at it. So, even this also is a unit cell. That means, in this case the 2 corners are on the yellow circles and 2 are on the white circles. Here again, if I take this motif there, this box which I have created unit cell, I keep repeating it like this, like that, I will be able to generate the whole lattice. Okay. So, that means what you find here is you can have still another way. What you see is this also is a unit cell there, because if I take this box which I have created here, I repeat that. So, I will be getting same thing here. I keep doing this again. So, I will be able to generate the whole lattice. So, what do we conclude from here is, that is, the choice of unit cell is not unique. For a given lattice, you may have n number of possible unit cells, but typically what is done is out of the all possible unit cell, the smallest one is taken as the unit cell there, because that is the kind of a norm we have, that is a kind of a convention we follow. Now, is this a unit cell? The answer to this is no, because if I take this as my unit cell here, suppose I try to translate that. So, we have white, yellow, white, yellow. If I translate that, it will be yellow, white. So, that means if I just have shown here, this is my one unit cell. If I do like this, so I am leaving some kind of a gap here. That gap is not allowed, because this unit cell must translate continuously. That means, if I have one box there, another one, it should continue. It should continue to generate the whole lattice. So, this is not a unit cell in this case. So, what you have seen is, in a 2-dimensional lattice, there are different possible unit cells. We have also seen one case where the unit cell is not the way it has been represented there, because it must be in a position to generate the whole lattice on translation. That is a basic premise we have. Thus, we can conclude that a unit cell of a lattice is that the small part of the lattice which, when repeated through space without rotation, gaps or overlaps, reconstructs the whole lattice. That is the way we will define a unit cell, because it is easy to do in 2 dimensions. That is why we have done it here. Having done this, we can probably move further, because that is one bit we wanted to. So, we have done so far is we have talked about what is a lattice. I am sure that you understand what is the meaning of a lattice. Lattice is a representation of an ordered arrangement. Thereafter, we have seen that a lattice can be represented further down in terms of small unit cells, which, when repeated or translated across the different dimensions, generate the whole lattice. Having done that, now let us try to see, when you talk about lattices, there are different variants of that. There are 2 variants. One is called as a Bravais lattices, one are non-Bravais lattices. Let us see what are these. The Bravais lattices are the ones where all atoms or the ions are of the same type and all lattice points are equivalent, which is very simple thing. What we have been doing so far was, say, the first few cases I gave you as examples, there were Bravais lattices there. And non-Bravais lattices are the ones where atoms, ions may be of different type. We have given example of sodium chloride, and some lattice points may not be equivalent in such cases. So, this is a representation of a Bravais lattices. All lattice points are equivalent and are identical. In this case, it is a non-Bravais lattice where the lattice points are not identical. So, they may be different. So, that is the basic difference between a Bravais and a non-Bravais lattices. Let us move further and talk about primitive and non-primitive unit cells. You will recall that for a 2-dimensional representation or 2-dimensional lattice, we realized that there can be more than one type of a unit cell there. Now, in such unit cells, there are 2 terminologies we have to follow here. That is, if a unit cell is such that the lattice points are only at the vertices, such a unit cell will be called as a primitive unit cell there. That means you see that, so this unit cell is such that all the vertices are occupied by a lattice point, and there is no other lattice point in the unit cell there. So this is a primitive unit cell. So is this one. This one is a non-primitive unit cell. What happens is, in this case, the vertices, that means the requirement is unit cell having lattice points only at the vertices is called a primitive unit cell. If you have a lattice point elsewhere also, then it is a non-primitive unit cell. So they are very small things, but they are very, very important there, because they have ramifications as we proceed further into three-dimensional lattices. So if we have a two-dimensional lattice and we are talking about a primitive unit cell, it will contain exactly one lattice point. Let us understand that. So we have a two-dimensional lattice here. So what you find is, I am trying to focus attention onto this circle here, which has been earmarked with a white boundary here. What you find is that this circle or this lattice point, so to say, is a part of 1, 2, 3, 4 unit cell, because the unit cell is just this small cube, small square here. So since this lattice point is a part of 4 unit cells, so in this unit cell, this has only 1/4 as the contribution there, and since there are 4 lattice points in this case and each one is contributing 1/4, we find that the total lattice points in a given primitive unit cell is just 1, exactly 1. On the other hand, if we have a non-primitive unit cell, it may have at least 2 points there, because one will come from here. Let us say in this case what you find is, so 1/4 here, 1/4 here, 1/4 here, 1/4 here, they will add up to give me 1 point here, and the 1 is right there inside. So there are 2 lattice points. You may have a situation where there are more than 2 lattice points are possible, but in case of a primitive unit cell, it will have only just 1 lattice point, and non-primitive at least 2 lattice points. So that is a basic requirement or basic outcome of our defining the primitive and the non-primitive unit cells there. Now let us move on to 3-dimensional lattices. Basically, a 3-dimensional lattice, as the name suggests, will be a representation of a 3-dimensional ordered arrangement. So we will have lattice points which will be spread over a volume, because it is not a line or an area, it is a volume now. That means they are in 3 dimension there. Now such a lattice arrangement is easy to visualize if I just try to use some lines through the lattice points. So we get, this is more familiar picture with us. So what you find is that this is a 3-dimensional lattice, and as in case of 2-dimensional lattice, we will have a similar thing here, that is, we will have a unit cell which when repeated in the 3 dimensions are going to give me the whole lattice. That means if I take this unit cell here, which is given in red lines here, so if I take this box, repeat here in this dimension, go backwards, go upwards, I will be able to generate the whole lattice. So we will have a unit cell here also. So a unit cell in 3 dimension is characterized by 6 parameters now. You remember that in case of 1 dimension, we had only one requirement, just a distance vector. In 2 dimensions, we needed 2 distance vectors and 1 angle between them. In 3-dimensional lattice, 3-dimensional unit cell, we need to characterize in terms of 6 parameters. There will be 3 distance vectors, that means what is the A dimension, B dimension and C dimension, and what are the respective angles between them. Let us see how are they defined. So what you find is, so there is a repeat distance in this direction, say A vector, a B vector and a C vector, and also we got angles. So the angle between A vector and B vector will be called as gamma, between B and C is called as alpha, and between C and A will be called as beta. That is a kind of terminology we have, that is a kind of convention we follow. So essentially in 3-dimensional vectors lie along the edges of the unit cell and they are designated as A, B and C, as I just mentioned. Now further, in the 3-dimensional lattice, you will find that each unit cell will be bounded by faces. Okay. So these faces also they follow a terminology here. A is a face which is having edges defined by lattice vectors B and C. Let us see here. So you have a unit cell here. So you have the vector B and C. So any face which is created by these 2 vectors will be my A face. So that is because typically what you see is, you see that A, B, C, alpha, beta, gamma. So A phase will be between B and C, B phase will be between A and C, and C will be between A and B. Okay. So, that is how it is done. So, B phase is between C and A and C is between A and B. So, you just take ABC, remove one, the rest of two are going to define that particular phase. So, the interfacial angles of the unit cells are defined as follows. That means, angle alpha is the angle between the two edges B and C, beta is between edges A and C, and gamma is between edges A and B. And another important thing is that each unit cell in a space lattice basically is a 3-dimensional lattice. Okay. So, each unit cell in a space lattice is identical in size, shape and orientation to every other unit cell. That is what we had in case of 2 dimension also, or even in 1 dimension. In 1 dimension, each lattice point has got identical neighbors there. Same thing holds here also. A given unit cell will be identical no matter which unit cell you pick up from the lattice, it will be same. Okay. So, that is the meaning of this statement here. Now, this is important here. The translation of a unit cell along the 3 dimensions generates the whole lattice. Let us understand this. I take a unit cell, I translate it along say A direction. Okay. So, what I get is a row. I take this row and then translate it in the second dimension, the B dimension. I generate a layer. I take this layer and go in the C direction. I generate a whole 3-dimensional lattice. So, that is the kind of relationship between the unit cell, a row, a layer and the whole lattice there. Now, let us see what have we done in this whole session. Let us try to summarize that in terms of a picture. You have a small unit cell builds up a space lattice, and if I take the space lattice and all lattice points I substitute with the suitable motif, I will get a crystal structure, and that crystal structure when grows to give me the crystal I am talking about. So, that kind of relationship, because what we are trying to do is, we have talked about crystals in the previous session, we have seen a lot of crystals with us. So, if you just go deep into that, if I suppose I can somehow zoom into a crystal. So, what I am going to see at the molecular level is something here, and this actually is something which was proposed by Hoy. Because means the ordered arrangement we have in the macroscopic world as a crystal, same is dependent or is built upon on the something which is very, very fundamental, the unit cell. So, that is the kind of thing we are talking about there. So, basically what we have done is, in this whole session today, what we have done is, we started with reviewing our contents of previous session. Thereafter, the basic crux of today's session is that we discussed how to represent the ordered arrangements in 1 dimension, 2 dimension and 3 dimension, and then thereafter we explained and differentiated between the meaning of a lattice and the crystal structure. I am sure that is suitably clear to all of us. Then thereafter we explained the meaning and the methods of identifying the unit cells in 2 dimension and 3 dimensional lattices. So, we have to understand that it is the unit cell is such which when translates generates the whole lattice. That is a basic premise. And we have also defined towards the end the parameters, that is the unit vectors and the angles between them, they are used for defining the unit cells. In the next session, we will move further into that. We will talk about Bravais lattices in 3 dimension, and we will spend some time on analyzing the cubic unit cells particularly, because in this course we are trying to we will talk more about the cubic unit cells. So, we will try to go a little deep into different aspects of cubic unit cells, so that we can